In our last video, Peter Holst described some of the benefits of a knowledge-driven product development process. In this video, Peter will discuss how you progress from simple scoping models into a full digital twin and some of the beneficial outcomes that can come from these tools.
But with a simple model, you often see that where do you need to be working, and now you can begin to focus your testing in that area where you expect to find a robust solution. If we have data that tells us one thing and a model that tells us the other thing, and they don't agree, then we know that either the data are being collected or measuring something in a way that's not representative, or the model is not right. But we strive for a scenario, a situation we strive to be in this place where we have model data and analytical data and empirical data that are essentially aligned.
Yeah, talk more about that. Talk more about how that process progresses. So you start off with simple. You break down the design into your components or subsystems, and then you start off with simple scoping models, and then those models can and do progress up to a full-on digital twin. So you can talk using the analytical and empirical along the way to help inform each other. But the ultimate goal is to have, if you so desire, a digital twin. Tell me about some of the things that you can do with that, either at the subsystem or full system level. I think that's pretty interesting, especially when it comes to the benefits you can get from moving into scaling, the ability to iterate virtually versus having to do it empirically.
Yeah, one of the great things about an analytical model as opposed to a physical model, that it's really easy to tweak the inputs. It's really easy to drive a characteristic to a particular extreme of tolerance, or a use case extreme like high temperature, that sort of thing. As one has the inputs that allow you to drive the parameters to a space that's consistent with those extremes. I'm talking about temperature, for example. So temperature is a great thing, where a great example is something where if perhaps, for example, you have an elastomer or a seal in your system, and you need to understand, well, how do the characteristics of this elastomer respond to differences in temperature? And you don't try to necessarily do a sort of a very low level model. In this case, you probably would try to understand, how does the durometer depend on temperature? And you might test a simple test in a simple environmental chamber kind of environment. And now you have a characterization of durometer versus temperature. You can use that in your analytical model. But now you have inputs into your analytical model that are empirically derived, and you strive for agreement at sort of higher level until you build out this sort of digital twin, which now allows you to say, okay, my digital twin and my physical embodiment are in agreement at one or several readily accessible parametric configurations. Now you can do really powerful stuff. So now you can begin to use your analytical model to do corner case studies, do sensitivity studies. You get a sense of how the response is, what is the response to variation in inputs. And that's just a fact of life and reality, that all inputs will vary. I mean, there's a reason why components have tolerances. It's because nothing's going to be perfect. And when you begin to think about very high volume manufacturing with multi-cavity plastic injection molded components, and you think about some number of like 2 to 8 or 10 or whatever number of components is, and begin to appreciate that now you've got, well, I've got 8 parts, 8 cavity tools. I mean, the combinations of components that go into those assemblies is monstrous.
And then you can do things like Monte Carlo simulations that allow you to scale virtually, and over thousands of parts, tens of thousands of parts, and you can explain that a little bit so the audience can understand what the power of that, and to be able to get an understanding of where you sit on the design surface, and how close you are to cliffs, or how robust your design is, especially if you're going to scale. Just talk about that a little, because I think that's a massively powerful tool that this approach brings.
Yeah, so there's the concept of a response surface, and you want to understand what is the response surface of your design to variation in inputs. And you'd like that to be a nice sort of topographically flat surface. Okay, there's some curvature, but you'd like to not have big cliffs or be right next to a big cliff, figuratively or literally. And so what you want to do is you want to understand how to shape the surface such that it's robust to variation in inputs. And one of the things you can do if you have a very nice analytical model is you can begin to build virtual devices where you begin to select components from their permissible tolerance space, and recognize that things have a distribution, most often Gaussian. For sigma, CPK 1.33 is pretty typical for manufacturing processes. And so you allow these components to vary over that range, and recognize that most of them are going to be pretty close to the middle. And the instances where you're selecting 8 different parts, all from some low limit extreme, is very, very small, vanishingly small almost. So you don't necessarily need to do a worst case design where your design accommodates all these limit conditions, because they're very, very small probability events. And so that gives you the ability to more effectively develop your design such that it's cost effective, such that it meets spatial constraints, meets battery power, battery life expectations, and so on and so forth. And you accept that your yield is not going to be 100%, but it's going to be 99.9% or 4 nines or 5 nines or whatever it is. Those things are measurable, and you can learn these things by as Moran mentioned, running a lot of Monte Carlo simulations, which are quite inexpensive computationally and very fast. So you can build tens of thousands of virtual devices and test those and see what the characteristics of the outputs are. And the other thing that's really powerful here is I think it really compels you to think about what is important. Like one of the things I sometimes say is that you build a prototype and you sort of from a top down or design by analogy method, and you put it on the bench, you say, look, here's my prototype, it works. I believe that oftentimes you don't really know that it works. And I say, and I don't mean this pejoratively, but it looks like it works. You think it works. You want it to work. So you
right
device, but you don't really know. There's a lot you don't know about it. For example, you don't know, is it like the only working device that I'm ever going to build? Or is it right close to a corner, like close to a cliff? And without going through the exercise and the process of building a model that informs you as to the characteristics of the design, you'll never really know that. And there just really isn't any practical way to say, okay, now I got one, okay, I'm going to tool up and I'm going to build 10,000 of these things, and then I'm going to test all 10,000 of them, because it just isn't practical to test 10,000 of them, and you can't drive the tolerances to the corners that you're going to get when you start building multi-cavity tooling and building hundreds of thousands or millions of them. You can't get there.
We've discussed this in the past. So there's also the opportunities that come along with the KDPD approach in terms of being able to pick a cheaper material, or make your design less robust, use less material. Can you talk about that a little bit as well?
Sure. I kind of alluded to it earlier in that you may come to a realization that the certain components, certain elements of your design are overly conservative or overly robust, or this thing is thicker, the wall thickness is greater than it needs to be, or I have more battery power, more battery capacity than I really need, or things like that. And it's not about sort of marginalizing your design, but it's about taking cost out of components or elements of the design that don't really buy you anything, that don't really return any value for what you're putting into them. And without doing these kinds of models, you're guessing, and you're just saying, well, I don't know how much battery capacity I need, so I'll just put in a really big battery. Or, I don't really know how much wall thickness I need, so I'll just make it really thick. I know that people think about it more than that, but it's really powerful to have a model basis for your design decisions. And that way, there are other sort of things that result from this. And one is that you argue less about opinions and more about facts, and
Right. Well, we talked about that as well.
I
mean, one of the things that this approach allows you to do is get rid of confirmation bias that may be part of an engineering design team, where either somebody due to their experience level or their title have an undue influence on the design team in the direction that they're going, just because they feel that's the right way to go. Whereas this is more data-based, right? It's more data-driven. You go in a certain direction because the data is telling you to go there. And anything more you want to say about that?
No, I mean, that's absolutely true. And, we trust the data, and I think we're appropriately skeptical about it. And we make sure that we build our models in a way that's reasonably robust, that we test our assumptions. We make sure that that when I allow certain terms to blow up, then the result blows up. And likewise, when we do testing, we try to make sure that we have pro controls, that we interleave our subjects, and we do all these things that help to mitigate or help to guard against inadvertent trending in data, because the technique of the tester improves, or the time of day improves. Or we used to make a joke about an aerosol drug delivery that you have to make sure that we're not seeing effects that are subject to the phases of the moon and that sort of thing. So
Right.
really making sure that you're doing testing in a good way that mitigates against inadvertent trends in the data, and appropriately controlling your experiment.
Great. Anything else you want to say in terms of KDPD, or it covers it? I think it's the approach is designed to basically do a lot more upfront work that is typical in a particular design, or a design as opposed to a design by analogy approach, right? To get a lot better understanding, a much more robust design, one that you have better knowledge on, and you can have a lot more confidence in, especially when you go to scale. Or do you anything you want to add just to sum it up?
Yeah, just that it's often very tempting to say, well, I just need one device, just build me one as quickly as you can. And I understand the value proposition there, and very often, you need to be able to respond to investors, or you need to be able to put something out there for your client to say that, look, here's a design solution. But I think that in the long run, while it appears to be slower at first, pursuing a model-based design approach is often, if not always, faster than, unless you get really lucky, unless you're really good, it's going to lead you to a better outcome more quickly in the end, and avoid a lot of downstream iterations that look like really open-ended kind of casting about for solutions. And so it's a form of insurance in a way.
Great. Well, thank you, Peter. I really appreciate your time. And thank you, audience, for joining us. This is going to be a series of podcasts, this Drive to Knowledge podcast. We are going to explore the KDPD approach. Our next in the series is going to be called KDPD, the nuts and the bolts, where we talk about the specifics and how you set up a KDPD approach and how you follow through on it. That will probably be 1 or 2 different podcasts. We're also going to delve into some case studies, as well as have some Q&A sessions with some of the design industry experts, particularly on drug delivery devices. So please like our podcast, and we thank you for your time. Thank you again, Peter.
Thank you, Ron. Thanks, everyone, for watching, and look forward to delivering more.
Great. Thank you.